Okay, aromatics. Aromatics. Substituent effects. Good to go? These are divided into different groups. Group 1. Group 1, strong activators. Okay? Atoms and lone pairs other than halogens, such as oxygen and nitrogen. Name of this compound. Yes, anisole. Anisole. What type of group is the methoxy? Well, the ring is bonded to an atom with a lone pair. It's not a halogen. That's a group 1. It's an activator. The methoxy makes the ring more active towards the EAS reaction. More reactive than benzene. Okay? Because it's a donator. Because it's a donator, it's more active than benzene. All right. There's two different ways to sort of show the donation. We can show it from the neutral molecule, or we can show it by working with the carbocation of the sigma complex. You're an intermediate, charged intermediate. Here, let's just show it from the neutral compound. Can we draw resonance structures here? When you have a lone pair that's conjugated, that's a great place to start drawing resonance structure. Lone pair conjugated. Right? Anytime a lone pair is next to a p orbital, we're going to want to be in a p orbital. These electrons, move them down and move these out. Resonance structure. Yeah? We can keep going. These electrons can move down, and we can move these out. And we can move these electrons here and move that pi bond out. Resonance structures. This illustrates the donation of the lone pair into the ring by resonance. It makes the ring more electron rich. Hybrid here. If you could actually see this compound, it doesn't look exactly like that. Because there's actually double bond character between the O and the carbon. We don't see it there, but we see it over there. Same thing here. Double bond, single bond, single bond, single bond. Is it single or double? Well, it's somewhere in between. And that's the same for every carbon-carbon bond. The electrons are all delocalized in there. This pi system, it's like water in a garden hose that's been tied off at each end. The water spreads out all in there. This is partial plus. And which atoms of the benzene ring are partial minus?
One's with the anion.
Ones with the anion. What's their position compared to where the methoxy is? Ortho and pair. Ortho to the methoxy, para to the methoxy, ortho to the methoxy. Which carbons of the benzene ring are most electron rich? That one, and that one. We see from the resonance structure. The hybrid comes from assessing your resonance structures. If you could look at anisole, it looks more like this with the electrons all spread around like that. At high electron density here, here, and here as a result of the methoxy group, The oxygen of anisole actually has a little positive charge. Okay? It's the old resonance structure discussion. Later on, we'll call this an ortho-pair director because it puts most electron density at the ortho and pair positions. Okay. Something else said here. This is resonance. All that's resonance. What about induction? Is oxygen donated or withdrawal by induction?
Withdrawal.
Withdrawal. Induction is electronegativity. Oxygen's more electronegative than carbon. All right? I'm oxygen, you're carbon. Oxygen pulls more. Pulls more by a single bond, induction. But at the same time it's pulling, it's got this lone pair. And it donates the lone pair by resonance. Okay? The donation by resonance is very strong and is the predominant effect with these guys, oxygen, nitrogen. So it pulls and donates. But what's its net effect? Donate, because the donation by resonance is a predominant overriding effect. That's these guys that are like O and N are most common. Any atom with a lone pair other than halogen. Because ultimately we want to know the net effect. Because often groups can do both, donate and withdraw. The net effect here is to donate. Group 1, net donator. And it's strong because it's resonance. It's the strongest. Group 2 are weak activators or donators. There's actually two types of groups here. One is a conjugated pi bond. For example, if you have a benzene ring with an alkene conjugated, you can draw resonance structures here. We don't have a lone pair. The pi bond can be moved and this pi bond can be moved out. That would give this resonance structure. And we start putting electron density in the ring as a result of this group. And we can do additional resonance structures. We can move it here. And we can put the minus on ortho, para, and ortho. But this is not as strong of a donation because there's no lone pair out there. And so thus we call it a weak resonance donation compared to the lone pair resonance. Now, this again is just starting with the neutral compound like we did with anisole. We could look at an intermediate cation. For example, if this brominates, and if the bromine goes ortho, that would lead a cation here. Can this group stabilize the cation? Yes, by resonance. So this group is going to stabilize the cation and make the bromination easier and faster. So this is working with a cation here as opposed to just working with the neutral compound. This group stabilizes the cation by resonance. But it's not as strong as a lone pair. Weak resonance donation. The other group that falls here is your alkyl groups. like a methyl, ethyl, propyl. Now, a methyl group has no resonance. It has no p orbital, it's sp3. So it only has induction. How does a methyl group, what's the induction of a methyl group? Donation or withdrawing? As we learned in organic 1, an sp3 carbon donates by induction. Okay? It donates by induction. You say, well, they're both carbons. There's no difference in electronegativity, right? But we just have always said an sp3 carbon donates by induction. That's why a tertiary carbocation is more stable than a secondary carbocation. Again, consider a sigma complex. Up there I didn't show it, but if you react with iodine, if the iodine adds para, we're going to get this cation, right? Here, cation, iodine here, cation here. Resonance though. Draw resonance structures, additional resonance structures. I don't think they're drawn, are they? Windshield wiper down. We can windshield wiper these up. Those are our resonance structures, like we showed on the very first page for any sigma complex. You've got to be able to get your group on and then be able to do your resonance. Does the methyl group affect that? If we took the methyl off, would it be just the same, or is the presence of the methyl?
Presence of the methyl stabilizes that carbocation.
Any particular structure help illustrate that best?
The second one.
Right here. Tertiary. The true structure is a blend of all these. The positive charge that falls on this carbon is essentially tertiary because you got the carbon. And so our hybrid has some tertiary character as illustrated by this resonance structure. Now we can make this even better if we had a methyl at each position. If we had a methyl here, here, and there, make all your cations better. And 3 methyls would be better than 1. But 1 methyl is better than 0 because methyl is a weak donator, but induction is a weaker effect than resonance. Resonance is a stronger. Group 1 has resonance. Actually, the pi bond up there has resonance, but that resonance doesn't have a lone pair, so it's not as strong as group 1. So there's 2 that fall here. Both of these, an alkene like that, or an alkyl group. Weak activators or donators. Yes, that's right. Toluene is more reactive towards EAS reactions than benzene because of the methyl group donating by induction. Question?
Can you have a hydride shift when the carbocation is ortho to the iodine?
You could, but then that product will never become aromatic because then it will have 2 H's on 1 carbon. So it's not going to migrate that way. You're going to lose your aromaticity. Okay, group 3. Group 3 are, okay, 1 and 2 are activators, 3 and 4 are deactivators. But group 3 is a weak deactivator. Okay? Here's where the halogens fall. Like group 1 atoms, halogens both withdraw inductively and donate by resonance. Induction. Chlorine's more electronegative than carbon. Okay? Pulls by induction. Withdrawing. But it can donate by resonance. We can do just like we did with anisole. Lone pair, just like this. Resonance. We can draw more resonance. So it can do both. But which is the major effect with halogens?
The induction.
With halogens, the induction is the major effect because halogens are so much more electronegative that effect is greater. Since this effect is greater than this effect, it's a net withdrawer. And thus it's deactivated. Chlorobenzene is less reactive than benzene towards an EAS reaction. Because when we form the positive charge in the ring in our EAS mechanism, the chlorine, what's its net effect? To withdraw. But withdrawing from a carbocation doesn't help the carbocation, it hurts it. But it can do resonance, and the fact that it can do resonance will help with the directing effect. Because this still puts more minus ortho and para. All right. And because of the resonance, that's why it's only a weak deactivator. Because it sort of counterbalances some of that. All right? Now, group 4 is strong deactivators. These are going to be electron-poor atoms with no lone pair. If the atom bonding to the ring has a lone pair, it fits into one of the previous groups, like group 1 or group 3, halogen. What are examples of electron-poor atoms? The nitro group falls here. Benzene ring bonded to the nitro group. The nitrogen, do you call that electron-poor? It's actually a positive charge. Does the nitrogen of a nitro group have a lone pair? No. So it fits that. Okay? Sulfone, the SO2 group. This could be R or maybe OH, like a sulfonic acid. The sulfur has no lone pair, and it's electron poor because it's bonded to these electronegative atoms. Carbonyl, very common. The carbon is electron poor because it's bonded to the oxygen. And the carbon has no lone pair. The cyano group, or nitrile. The carbon is electron poor because it's bonded to the nitrogen, and the carbon has no lone pair. As they have no lone pair, they can't donate by resonance. Also, you're not going to do any pi bond resonance either, because you would never move this pi bond in for resonance because you'd leave the oxygen with no octet. So there's also no resonance from pi bond like we did with that alkene. There's no resonance at all here. So there's no donation. They only withdraw inductively. Because if this group is bonded to the carbon, it would be a positive nitrogen. That nitrogen is going to pull. If this is the benzene ring, it's going to pull. This sulfur is actually partial plus because of the dipoles here. It's partial minus, partial minus. And if it's partial plus, it's going to be greedy. It's going to say, hey, I'm partial plus, I got to have some electrons. This carbon, partial plus, so it's going to pull on the benzene ring. This carbon, partial plus, so it's going to pull on the benzene ring. Okay? They all pull because they're electron poor. These are your strong deactivators. There's no resonance to counteract the withdrawing. Nitrobenzene is much less reactive than benzene towards an EAS.
If you have a long enough like carbon group with like a sulfone and a carbonyl, could it really minimize the withdrawing effect?
What do you mean a long group?
Because like a long carbon chain would be able to donate a lot of So would that like counteract?
Well, I mean, what do you mean by long? You're saying something like this?
Or long where it's the R group, like that's it's bond, you know how it would be bonded directly to the benzene and there's a long R group.
You mean here, but the R group is just long?
Yeah.
No.
It wouldn't.
No, you still, you just, in all these examples, you look at what it's bonded to. Okay? That's what I'm saying. The atom it's bonded to, this is an electron poor atom with no lone pair. That's group 4. This is removed from the benzene ring. You just want to focus there. I don't know of any really examples to tell you where something out here is going to override. You want to look at what's bonded to the benzene ring. Now, we can focus in on just the nitrogen, but you sort of just know that the nitro group, the nitrogen is bonded to the benzene ring, and so we just say the nitro group is strongly withdrawing. Nitro group is a group 4. A carbonyl is a group 4. Sulfone is a little less common. And cyano group, yeah. But the nitro group is probably the most common here. It's just a common group that's withdrawing. Because you see nitros a good bit on rings. But also carbonyls are pretty darn common. Okay. Review. Something like phenol. Phenol is more reactive towards EAS. Why do I keep saying towards EAS? Because in about a week, some of these things are going to be reversed. You got to be careful when you say phenol is more reactive than toluene. What do you mean, reactive towards what? Right now we're talking about EAS. All this applies to EAS. Phenol is more reactive than toluene. Does that make sense? Well, that's a group 1 substituent. While that's a group 2 substituent. Toluene is more reactive than bromobenzene. Because that's a group 3. And bromobenzene is more reactive than the benzene with the methyl ester. We don't know the name of that. If that was an H instead of a methyl, it would be benzoic acid. It's called methyl benzoate. Methyl benzoate there. Where does benzene fall here? If you put benzene up here with these 4, where does it fall?
Right in the middle.
Yes. Yes. Benzene falls here. Group 1, group 2 are activators. Because the cation that's formed in the ring is stabilized either by induction or by overriding resonance, benzene. Here, the bromine hurts the cation because bromine's a net withdrawer. But it's not as bad as that because at least bromine has a lone pair and it can have some counteraction by resonance donation. That ain't nothing but a withdrawer. That's going to be the worst carbocation in the ring. By the way, so an ester is a withdrawing group. You got to be careful about that because what functional group is this? Also an ester. But it's switched around. Here the ester oxygen is bonded to the ring. Big difference. This is actually, what type of group is this?
Is that a group 1 activator? Is that a group 1 activator?
It's group 1. We have an atom with a lone pair that's not a halogen. This compound is much more reactive towards ES than that one. Because here the oxygen is conjugated with the ring and acting as a group 1 donator. Above, the carbonyl is conjugated with the ring, acting as a group 4 strong deactivator. All right? So next time you're out and someone says, hey, an ester is a strong withdrawing group on the ring, you got to, well, hold on. It could be a donator, depending on how it's sort of arranged. That's an ester too. Yeah? Lots of rate data is available or known to illustrate these things. Anisole is 10,000 times more reactive than benzene towards an EAS reaction. Actually, specifically, this is for nitration compared to benzene. Anisole nitrates 10,000 times faster than benzene. Toluene nitrates 25 times more reactive. More reactive, but it's mildly activated, right? It's a strongly activated. Anisole will nitrate without much of a catalyst and without much heat. Toluene may require more true catalyst and maybe a little longer reaction. Nitrobenzene nitrates, if you try to put a second nitro group on, it's 100,000 times slower than benzene. The first nitro group will go on. The second one is much more difficult to go on because the nitro group, once it goes on, then serves to deactivate and make the second one more difficult. Strongly deactivated, wouldn't you say? What about, can these effects be additive? Yes, we can just sort of add them up. Here's 4 compounds here. Which of these 4 would be the most reactive towards an EAS?
Second one?
The second one.
I think the second one. How'd you get the second one?
It has
Because
a
that's strong activator.
and a weak.
Strong. Strong activator and a weak deactivator. What is this?
A strong deactivator.
Strong deactivator
Weak activator.
and a weak activator.
Does the arrangement affect that anyway? Between the one that's meta, the strong, the most reactive one, if it was.
It does, but if that was brought in here, it'd probably make it much more difficult.
Okay.
And it shouldn't affect it in the example I'm giving. For example, I could show you the same compound to put the chlorine here. We're also not saying where are we trying to put the group. So it's sort of general here, and we can do that very general as we're doing it. Just compare these two. I mean, that's a strong and only mitigated by a weak deactivator. This is a weak mitigated by a stronger deactivator. So you see how they sort of add up. You can just kind of add them up in your thought process. There's more activation here. What do we have here?
Deactivator.
Weak deactivator. So if you're comparing these two, this just cancels each other out. And you're just left with an activator here. So this should be more active, more reactive. And then over here, we can actually rank these. Because this is a strong deactivator. Most activated should be this one. What's next?
Probably either 3 or 4.
Well, 3 and 4 is easy. Which one is more reactive?
3.
This is more reactive than that.
Lone pair.
Now that ain't as reactive as benzene, but it's more reactive than that. So that's a group 3. How does this one fit in? We'll compare this one to the one on the end. They both have strong deactivators, but that one has a weak activator. So this should be more reactive than the one on the end. What about this one in bromobenzene? That's kind of a tough call there. I think definitely this is 4.
With the bromobenzene, because it can
Which is more reactive, this first or the third?
with the third, because it has some resonance stabilization.
Tell me again.
Say the third would be
More reactive. Unless I'm missing it, it looks too close to call. Because this strong deactivator is sort of mitigated by some activator. And maybe takes this down from strong to just weak. I don't know that I've ever ranked these. The question here is really just to choose the one that's most activated. And the one that's most activated is the one we labeled 1. Least as possible 4. These two are a little bit too close for me. And I don't know that we can do it. All right? So that's looking at sort of trying to add the effects up, and you can just do that. Of course, I would give you one that would be clear answer. I would never ask you between 1 and 3, because if I can't do it, I wouldn't expect you to be able to do it. Sometimes you just can't do the answer. You can maybe look it up and see if there's any rate data known for those 2 exact compounds. And if not, and if you really had to know for some reason, you could go to the lab and study yourself. Bromobenzene, what's the name of the other compound, by the way? First compound.
Which one?
That's right, paranitrotoluene. Right? Paranitrotoluene? See a common name there, toluene? Nitrobenzene is not a common name. Okay, that is activation effects. Now, you can, in your book again, they may divide these up differently. This table from some book, I don't know how many groups they had, but it's either more or less than my grouping. You can look at how they do it here. Okay? A little bit different. Okay, next is directing effects. Where is a new group going to go relative to an existing group? Anisole, we know it's much more reactive than benzene. But if you try to nitrate anisole, where's the nitro group going to go? It turns out that you get a mixture here. You get 45% of the orthonitro product. You get 55% of the paranitro product. And you get virtually none of the meta. Maybe a small trace. Certainly you get much more ortho and para. And you do get a mixture. Based on those results, we can say the methoxy group here is ortho pair director. It's directing the new group to the ortho and pair position. Positions. Yeah?
Dr. Stevens?
Uh-huh.
So if we had like a predict the product question, would we be expected to draw both to show that it could be in?
Yeah,
Okay.
you get both. You get a mixture.
Kind of like a racemic mixture, like before. Like, is it analogous to that?
Well, somewhat analogous. That's stereochemistry.
Mm-hmm.
This is regiochemistry. The two are regioisomers.
Okay.
The nitro group is bonded in different regions. They're constitutional isomers, not stereoisomers. Yes, it gives a mixture. Now, sometimes you can modify your conditions a little bit to get one over the other. Sometimes we will actually get more. And actually, the pair is favored here. Well, you say, of course it is. It's 10% more. But you also have to keep in mind that there's two ortho positions. If we had nitrated over there, it's the same product. So it's inherently twice as likely for the reaction to go ortho, because there's two ortho carbons. But you don't get twice as much. You actually get more pair, even though there's only one pair of carbon. So it actually does sort of prefer pair, if you consider the two carbon versus one. Why might it prefer pair compared to ortho?
The lowest energy state.
It can,
Well, that's sort of my question. Why is that the lowest energy state? Because the fact that it does implies that it must
it's
be.
because it can drain down through the
No.
The two big streets are opposite.
Perhaps, but we don't have rotation here.
Isn't it just,
Sterics. Okay? Because for the group to approach up here, that methoxy could get in the way. It's much more likely for the group to approach down here because there's no methoxy. So ortho, it does sort of limited by sterics. But you see, we're still getting 45% there. Again, perhaps because there's two carbons there versus one. But there are some reactions that are more para-favored. But in any EAS reaction with such a group, you're always going to get a little bit of the other. That's just Mother Nature has given us with these reactions. Ortho-pair directors, and you often have to purify and separate those. Sometimes the separation may be easy, relatively easy. Sometimes it may be very tedious. If it's very tedious, you try to make your product some other way. Yes, it's a somewhat flaw of ortho-pair directors, both. You'll see more as we go along. But you don't get much meta, ortho-pair director. How do we know this? Well, here's sort of the rules. And after we state the rules, you can sort of try to rationalize. Here we go. Any atom that can donate somehow will be an ortho-pair director. Which groups donate somehow? Group 1 does. Strong donation. Donate what? Somehow. Yeah. Group 2, net donator. Yeah, group 2 is ortho-pair director as well. What about group 3?
it's more.
It's a net withdrawer, but we're not talking about net. Can a halogen donate?
Yes.
Yeah.
Donates by resonance. It's not its major effect. It's not the net effect, but it can donate. Group 3 is also ortho-pair director. What about group 4? Did it donate anyhow?
No.
No.
No, we say group 4 can't donate at all. Here's a take-home. Groups 1 through 3 are ortho-pair directors. Group 4, which can only withdraw, is a meta-director. For example, if you take nitrobenzene and nitrate it again, you'll get 91% meta-nitrobenzene, or meta-dinitrobenzene. This implies that the existing nitro group is directing meta, because you only get you do get 7% ortho. That's a little bit high compared to like most textbooks will show you. And pair is, okay, this is actual real data. And that's actually odd. Why do we get so much more ortho than pair for those low ones over there, sterics? There could be some interaction there between the group. Sometimes sterics is bad, but sometimes that group may actually attract another group because of some IMFs or something. First thing is sterics. It's just too much crowding. At the end, predominantly meta. Would you agree? 91? And it's called a meta directory. And you would never say, hey, we're going to try to put a group ortho here. You would never devise a synthesis like that. Because if you do, you're saying, hey, I'm going to get 7% yield. And why would you ever devise a synthesis where it's going to be 7% yield? So I give you this, but this is nothing. Meta is your main product. And a lot of times we'll just say major product. For example, if you brominate this guy, bromine like an iron catalyst, it's actually a pre-catalyst, right? We expect the bromine to go meta. We expect, in this case, only one product, where the ortho pair is a mixture. So it's actually a cleaner reaction. It's going to be easier to get a single product out. And in terms of our prediction, we predict that as our major product. Where up here, we would predict that as a major product. And you would just not show these because they're typically the question is going to ask you to supply the major product. Down here, just an additional example, if we try to iodinate, you got to know your conditions, right? Iodination. What's the copper chloride doing in this reaction?
It's creating an I+.
Not a catalyst.
So,
What's it doing?
it's producing oxide.
Rodak? What's the copper chloride?
It's there to just make the I+, the I cation, iodine cation.
So it's serving as a
oxide.
copper chloride is a what? We know the bromine is what type of director?
OP.
It's group 3. Groups 1 through 3 are ortho pair directors. We're going to have two major products. Iodine's para and iodine's ortho. Copper chloride,
It's an
Oxidant.
it's an oxidant to oxidize the iodine to I+. Yes. It's stoichiometric. It's not a catalyst. It's going to be consumed. You're going to have a full amount. Because it gets reduced. It's reduced at the end. It's no longer the same thing. It's a necessary reactant, sometimes called promoter, but you wouldn't want to call it catalyst. Okay, why? Why do these groups act as they do? Kind of because from the resonance we saw, we can look at the methyl group as an ortho pair director. 3 different attacks. If the electrophile is essentially, we can say, added ortho, or if the attack occurs to react bonded ortho, it's going to leave a cation. We can do resonance. And we've already done this for the methyl. Remember, we had it here, we said tertiary cation. Well, look, here you go, it's in the box. There's your stabilization there. if we do that route. If we do para, okay, cation, resonance. Here we go again. You get that good resonance structure for your intermediate. But if we do meta attack, and by the way, you should be able to do every attack in the resonance structures for each attack. Okay, this is your EAS mechanism, intermediate. Okay, you can go different positions, understand your error movement. We're going to get cation here, here, and here. Did we ever get the good resonance structure where the cation falls on the carbon with the methyl? No. So that intermediate is not as good. You don't get the benefit of the methyl. So it's not going to go that way. But it will go the other two ways. And we can look at something with a lone pair, like aniline. Ortho attack, plus, plus, plus. Here, cation, right here. In this case, though, see, with the methyl, we can only invoke just induction. But here we can actually draw resonance. And we can get an additional resonance structure because of that lone pair donated. Same thing below. Cation falls here, additional resonance structure. Can you get the additional resonance structure meta? Positive falls here, here, and here. It never falls on the carbon with the amino group, so you can never do such a resonance structure. So you don't have the additional stabilization you do for when the orthopara. So it does not go that way. Your intermediate is not stabilized by resonance. Let's finish this up down here. Nitro group, which we know is a meta-director. Well, look at your attacks. Ortho. The positive does fall here. But that's actually bad. Why is that bad? Because the plus is falling on a carbon that's bonded to a positive nitrogen. You don't want those two pluses so close together. That also happens with the para attack. Bad in this case. So these don't occur. Why does meta occur? Not because the meta is good. It's because it's not bad. When it goes meta, the positive never falls on that carbon. It's three intermediates. That's an intermediate, that's an intermediate, that's an intermediate. Which intermediate is the best? The one that you get by meta attack. Not that it's good, it's just it's less bad. You really need to look at your resonance structures and your intermediates and see this what's going on here, okay? It's the old EAS mechanism, but the stabilization of the sigma complex by resonance, and then understanding how a group, we add a group to the ring, how it can influence this, both in terms of overall stability and in terms of then directing effect. Okay. At this point, we're ready to look at additional reactions, and we'll move to Frito-Craft, blue. Okay. Go back over here. We did sort of these. We're now ready to look at these, putting carbon groups on the ring. That's the blue handout. We'll be there on Friday. Okay. See some of you in lab.